Okay, so we just finished up basic geometry of circles unit. Unit 3 builds off of that, and I want to start off by reviewing some of those basic features of circles that we've seen. Of course, the most basic feature of a circle is the radius. Remember, we said the location of the center of the circle and the length of that radius completely define the circle. I mean, that's all the circle is defined as is a set of points that are a given distance from the center. That given distance is the radius. We defined chords, and we looked at the relationship between chords and the length of the arc. We defined central angles. That would be the central angle there. And the arc out here can be described in two different ways. It can be described by the angle. If this central angle here is angle theta, it could be labeled as that many degrees. Or it could actually be labeled as a length in centimeters, inches, whatever unit of length we want to use, whatever unit basically that the radius is in. And we looked at how that arc typically could be described in terms of radians rather than degrees for the angles. That 360 degrees, which is one complete revolution or turn of the angle, is equal to 2 pi radians, because that is the distance around a circle if the radius equals 1 unit. So the circumference is 2 times pi times the radius. Hence the 2 pi radians where the radius is 1. The area was pi times radius squared. And we had various formulas for arc length and area of a sector, area of a segment, and all that. We're not going to be so concerned about those anymore in the next couple of weeks here. But there are some features of a circle that we are very concerned with. Some of them we've talked about, some of them we really haven't yet. One is something, we know this is a diameter of a circle, but this is a special diameter. This is referred to as a reference diameter. And what a reference diameter is usually a horizontal diameter, and it's a diameter that other features of the circle are referenced from. We talked about navigation and direction before. Usually one end of that reference diameter is considered to be 0 degrees, and it goes around the circle from there, usually going counterclockwise around the circle for measuring angles. Every point on that circle, let's pick a point on the circle, that one right there in red. If I measure its distance from that reference diameter, now remember, distance from a point to a line is measured at a right angle like that. That distance is called the sine of that point. So every point has a sine. This point here, that has a much smaller sine. This point up here has a larger sine. Now the sine of a point can never be larger than the radius of a circle. So if the radius of this circle is 1, the sine can never be bigger than 1. As you can see, where the sine would equal the radius would be right here. If it's exactly above the center, then the sine would be exactly equal to the radius of the circle. Now, the sine going down, if it's below that reference diameter, that would be considered a negative sine. So the sine is bigger than the opposite of the radius, the negative radius of the circle. So it's within that range. We also had segments that contain points both inside the circle and outside the circle. Those are called secants. And we had lines that contained exactly 1 point on the circle, and all the other points on the line were outside the circle, that was called the tangent. Well, the reason we're reviewing those features of a circle is because they come together to define all of our trig functions that we're going to be working on next. And to define those trig functions, we look at something called the unit circle. Everybody thinks that our trig functions come from a right triangle, and they don't. They actually come from a circle, and they are applied to triangles. So a unit circle is a circle with a radius equal to 1 unit. Here's our circle. Try to make sure I get it pretty close to the center there. I'm going to go just a touch. There's our unit circle. It has a radius of 1 unit. This is considered the 0 degree point over here. So that 0 degree point, this spot right here, is called the initial side. All angles start at the 0 degree point and rotate around from there. So if I rotate, we rotate counterclockwise for positive angles, there I call that angle, we'll call it angle theta. Remember that theta, that's just a variable representing an angle, just like x or y or z for lengths. We use those theta, alpha, beta for angles. This blue line here is called the terminal side. That's where the angle, we start at 0 degrees and we rotate the degrees of the angle, that's where the angle ends, that's where it stops. And where that terminal side hits the outside of that unit circle defines a point that defines our angle. First of all, that arc there is another way of naming that angle. The length of that arc is the size of that angle in radians. I had my phone buzzing behind me. I had to make sure. So that arc length is the radians of the circle. That's how we use that conversion. That circle with a radius of 1 had that circumference of 2 pi. So 360 degrees was equivalent to 2 pi. But there are a lot of other important features. The distance from that point down to the horizontal diameter, the reference diameter, should label that. That is our reference diameter for this circle. That distance, we've already seen, we've already defined that from a point on the circle to the reference diameter is called the sine. So that would be, the sine of our angle theta. Now there are 2 other main trig functions. We know sine. One of the other ones we know is tangent. The tangent when we're dealing with trig functions is tangent to the circle at one end of that reference diameter. So there's one end of the reference diameter. The tangent would go like this. Where does it stop? Well, if we extended this terminal side out, where it hits that terminal side, that's where it stops. That length in green is defined to be the tangent of our angle. And now we have this piece over here that contains points both inside the circle and outside the circle. And a line that does that, or a segment that does that, is called a secant. So that length is the secant of our angle theta. Those are the 3 main trig functions. Sine of an angle, tangent of an angle, and the secant of an angle. Well, you might be thinking, well, we learned sine, tangent, and cosine, not sine, tangent, and secant. Well, we'll come back to why cosine is used as one of the 3 main ones in a little bit. But these are the 3 main trig functions, sine, tangent, and secant. And you can see their values just come from these different lengths of the actual features that have those same names on this unit circle, where we have this central angle here rotating from 0 degrees to the terminal side. So let's mention the co-functions. The co in co-functions actually means complement or complementary. So the cosine of an angle, let's just call it angle alpha, literally means the sine of the complement of alpha, of that angle. Well, where in our diagram up here would we find the complement? Since this is our angle theta down here, and we know that if we have a horizontal line and a vertical line, they form a right angle with each other. So that angle right there has to be a right angle. This angle up here is the complement of theta. So what happens is this is the main reference diameter, as we saw labeled over here. But this other diameter, the vertical diameter, becomes the complementary reference diameter. And it's that complementary reference diameter because whatever angle we have here, its complement is right there. So the sine of the complement goes from that point on the circle over to that diameter. That is the sine of the complement, or, as we said, the cosine. So I'm going to redraw a new circle because that one's getting a little cluttered. So here's my terminal side. Here is theta. This right here is the cosine of theta because this is the complement of theta. Since that is now the reference diameter going vertically, the tangent for that complement would look like that. That is the cotangent of theta because it is the tangent of the complementary angle. And of course the secant comes out like this. This distance would be the cosecant. The secant of the complementary angle of theta. So we have all of those triangles there. Now since this, a tangent forms a right angle with a radius, we know that's a right angle up there as well. This angle up here is actually theta, because this being a right angle, this is the complement of theta, that has to equal theta, because those three angles of the triangle add up to 180 degrees. The two non-right angles add up to 90. They're always complements. In any right triangle, that's my right angle, these two angles are complements because they have to add up to the other 90 degrees. Well, how did all of this come to be used on right triangles or on triangles at all? Because it's parts of the circle. But you might notice as you look at these parts of the circle, they do form triangles, and those triangles are right angles. So let's look at a generic triangle. Go all the way down here. A right triangle. And one thing that we mentioned when we were looking at similar triangles is if I have a triangle, a right triangle, if I know that one of the angles are the same, one of the non-right angles is the same, then I know all three angles of the triangle are the same. In other words, they're similar. So I can compare this right triangle to this right triangle. If they both have that same angle there, those are similar triangles. Well, let's look at this first one over here as a a main triangle that has dimensions on. We're not going to actually put those dimensions on, but I'm going to label the sides. We know that in a right triangle, the side that is across from the right angle is called the hypotenuse. That's the hypotenuse of that triangle. The other two sides are called legs. But we need to differentiate between the two legs. So the leg that touches or is next to the right angle is called the adjacent leg. And the leg that is across from or opposite the right angle is called the opposite leg. Let's take this triangle here and draw it as one of our triangles out of the unit circle. In fact, the one that I have highlighted here is the one I'm going to draw. This one right here. If I draw that triangle, this here is just the radius of the circle. So that is 1. It's a unit circle, has a radius of 1. This side over here was from the point on the circle down to the reference axis or reference diameter. That is the sine of theta. This side down here is a little trickier. Let's come up here. This side down here is going to be the same as this side up here, because that kind of forms a rectangle, because those are all right angles. So this length is actually equal to the cosine of theta. One more triangle I want to draw out. Actually, there's going to be a couple more, but I want to draw out this bigger triangle here, the one that uses the secant and the tangent out there. That triangle, if I draw it out, I'm going to scroll for some reason, feels like it. So this is still theta here. Now, this side is 1 unit. That's the side that's the radius of the circle. It goes from the center all the way out. So that's 1. This over here was the tangent of theta. And this, the hypotenuse, was actually the secant. It contained points inside and outside the circle. Tangent was all outside the circle except for this one point here that was on the circle itself. I can use those triangles now to define my trig functions because these are similar triangles. I am going to compare in this triangle the sine to the hypotenuse there, the 1. Now sine is abbreviated sin, so sine of theta compared to 1. Now I'm going to look into this triangle here at the corresponding sides. Well, the side in this triangle that corresponds to the sine is the opposite side. I'm just going to abbreviate that OPP. The side that corresponds to the 1 is the hypotenuse. I'm going to abbreviate that HYP. This is a formula. If you've had trig before, you probably recognize it. Sine over 1, we can ignore the over 1. Sine of an angle is equal to the opposite side divided by the hypotenuse. Let's look at the cosine here. And again, we're going to compare it to that 1. So the abbreviation for cosine is COS, and we're going to compare it to the 1. Well, the side in the other triangle that compares to the cosine is the adjacent side. So abbreviate that ADJ for adjacent. And the sine that corresponds to the 1 is once again the hypotenuse, HYP. Again, if you have had any trig in the past, you'll recognize this formula here as cosine is equal to the adjacent side divided by the hypotenuse. That's all we can get off of that triangle, so let's go over to the other triangle. Let's look at the tangent. Now, on this triangle, 1 is down here, so I'm going to compare the tangent again to 1. The abbreviation for tangent is TAN of theta compared to 1. Now, from the main triangle here still, the side that corresponds to the tangent is the opposite side. That's OPP. The side that corresponds to the 1 is the adjacent side, ADJ. Once again, you might recognize from your definition of your trig functions that you've memorized, tangent of an angle is equal to the opposite side divided by the adjacent side. Now let's look at the secant here compared to 1. The abbreviation for secant is SEC of theta compared to the 1. Well, the secant here corresponds to the hypotenuse of the other triangle, so that's HYP. The 1 still corresponds to the adjacent leg, so ADJ. And again, you probably recognize this trig definition. The secant of an angle is equal to the length of the hypotenuse divided by the length of the adjacent side. Well, there's 2 more trig functions to go, the cosecant and the cotangent. They come from this triangle right here. That triangle is upside down compared to these triangles. This is a right angle. This is our angle theta over there. This is the cotangent. And this here is the cosecant. This would be the radius, the size of 1 over here. So if I compare those, if I have cotangent, which is abbreviated COT, over 1, the cotangent corresponds to the adjacent side, 1 corresponds to the opposite side. That's adjacent over opposite. The definition of cotangent. Cotangent of an angle is the length of the adjacent side divided by the length of the opposite side. If we look at the cosecant, again, we're going to compare the cosecant to 1. The abbreviation for cosecant is CSC compared to 1. Corresponding to the cosecant is the hypotenuse. Corresponding to the 1 is the opposite side again. And that is our definition of cosecant, is the length of the hypotenuse divided by the length of the opposite side. Those are our 6 definitions of trig functions. Now you can ignore the over 1 over here because dividing by 1 doesn't do anything, but I put it in there so you can see that proportion for similar triangles that gives us those trig identities, those trig functions. I highly recommend you find a page in your notebook that's easy to find. Maybe go to the back page of your notebook and write those down so you can get to them easily, because you're going to need to refer to them a lot over the next couple of weeks. One of the things I want to point out here is the relationship between secant and cosine. You'll notice the secant is the hypotenuse over the adjacent side, and the cosine is the adjacent side over the hypotenuse. Well, they're reciprocals of each other. In other words, the secant of an angle is just equal to 1 over the cosine of an angle. So why does the calculator use cosine as our third main trig function instead of the secant? Well, we can substitute in because if we know the cosine, because of this relationship, if we know the cosine, we know the secant, we can just use the reciprocal, do 1 divided by the cosine gives us the secant. The other reason why the calculator uses cosine is because of the relationship between the cosine and the sine. Remember, if I want to find the cosine of an angle, let's say I want to find the cosine of 37 degrees, that is equivalent to the sine of the complement. The complement of 37, 90 minus 37, is going to be 53 degrees. So those two functions, the cosine of 37 and the sine of 53, are equivalent. The reason cosine gets used dates back before the times of the calculator, when we actually had tables. I've always had the calculator for doing trig functions, but my high school math teacher did make us, for about a week, use the trig tables. And it was about 4 pages in the back of our math textbook that listed all the angles from 0 degrees up to 90 degrees, and actually listed some of the decimals in between. And you could find the trig functions off of that table. Well, that table only really needed to list the sine, because if you listed the sine you could find the other trig functions. If I wanted to find the cosine of 37 degrees, I had to use this idea that of the complements. I found the complement of 37, which is 53, so you looked up the sine of 53, you had the cosine. So the reason they used cosine instead of secant is cosine could be found on the same trig table as the sine without having to make a new column for those new values of that new function. So when they started programming the calculators to do the trig, they did the same thing. They programmed the algorithm for the sine into the calculator, and then they just programmed the cosine to use the sine algorithm for the complementary angle. Kind of a long-winded answer for a simple concept. It's that relationship between sine and cosine is why we use the cosine instead of secant as our main functions. So anyway, hopefully you've got those 6 functions recorded somewhere where you can reference them. Let's take a look at a triangle here. There's my right triangle. I'm going to call this angle A, B, and C. Typically we refer to as the right angle as being angle C. That's just standard to do. And let me put some numbers in here. Let's call this 15 inches, 20 inches, and 25 inches. And yes, that is a valid right triangle. If you do a squared plus b squared equals c squared, it should hold up. It will hold up. So if I ask you to find the sine of angle A, well, remember the sine is the length of the opposite side over the hypotenuse. Well, the hypotenuse is this side. It is the side across from the right angle. That's always the hypotenuse. But the opposite side and the adjacent side depend on which angle we're looking at. According to angle A, which is right here, the opposite side is this one over here. That is the opposite side from angle A. So if I look at the cosine of angle A, oops, I should finish that problem off. The sine of angle A would be the opposite side, 15, over the hypotenuse of 25, which is going to give us 0.6. Now let's come back to the cosine of angle A. Cosine is adjacent over hypotenuse. Well, for angle A, this is the adjacent leg because it's the one touching angle A. So that length, adjacent length, is 20 over the hypotenuse of 25. That divides out to be 0.8. Well, that's wonderful until we look at what is the sine of angle B. So angle B is this one. Sine is still opposite over hypotenuse, but if we're looking at a different angle, the hypotenuse always stays the same because it's across from the right angle, but the opposite and adjacent legs switch depending on which angle we're looking at. If we're looking at angle B, this is now the opposite side. So that would be 20 over 25, giving us 0.8. That 0.8 probably looks familiar. The cosine of angle A was also 0.8. Well, why would that be? Well, because this angle and this angle here have to be complements. Because this is a 90-degree angle down here, and the triangle adds up to 180. In any right triangle, the other angles other than the right angle have to be complementary. They have to add up to 90 degrees. So it makes sense that the cosine of one is equal to the sine of the other. So the cosine of angle B, which would be adjacent over hypotenuse, well, from angle B, this is the adjacent leg, because it's the one next to it. So that would be 15 over 25, or 0.6. Again, it makes sense that that is the same as the sine of angle A. The cosine of one is the sine of the other. Tangent of angle A. Tangent is opposite over adjacent. So the opposite side is the 15. The adjacent side is the 20. That divides out to be 0.75. The secant of angle A. Secant is hypotenuse over adjacent. Here the hypotenuse is the 25, and the adjacent for angle A is 20. 25 over 20 is 1.25. The cosecant of angle A. Cosecant is hypotenuse over opposite. So the hypotenuse is still the 25. The opposite is the 15. 25 over 15 is 1.667 is my cosecant for angle A. Typically, now the first several functions I divided out here came out to be, they terminated decimals after 1 or 2 decimal places. If they don't terminate, it is typical to round our trig functions to 4 place values. This is 1, 2, 3, 4 non-zero place values. What do I mean by non-zero? Well, let's do the tangent. Actually, the cotangent, I should say, isn't going to come out any better, but I'll show you. Cotangent of angle A is the adjacent over the opposite. Well, the adjacent side is the 20 over the opposite side of 15. That's 1.333333333. But we'll stop after, since there's a 1 in front of the decimal point, we'll go 3 after. That gives us 4 total place values. If I go, let's do the, I don't have anything that's going to come out small there. If I'm looking at a different triangle, let's do this one here, where this is 5, 12, and 13 units, and here's my angle A. If I find the sine of angle A here, sine is opposite, which would be the 5, over the hypotenuse, 5 over 13. Well, that is 5 divided by 13, 0.3846. Notice I went 4 places after the decimal there. That's because it's only a 0 in front. So if it's a 0 in front of the decimal point, we'll go 4 more places after the decimal point. If we have a 1 or something other than 0 in front of the decimal point, we usually only go 3 places after the decimal point. Just so you're aware for rounding. The homework may tell you to round differently, but that is the standard convention. Well, we've defined all these trig functions off of the triangle itself. How would we calculate them with a calculator? What if I just ask you to find the sine of 52 degrees? Well, on our calculator, we have those buttons, sine, cosine, and tangent. The sine of 52, most of you have forward notation on your newer calculators. So you'd hit just the sine, type in 52, close your parentheses, and hit equals. Now, I think 0.7880 is correct, but I should always double check the mode on my calculator. You go to mode, and there's radians and degrees, and mine is set to degrees, so that is correct. So the 0.7880 is the correct sine for 52 degrees. I want to do the cosine of 11 degrees. I just hit cosine 11. I get 0.9816. On a related note, the sine of 79 degrees, I don't even need to punch this in the calculator. I know it's going to be 0.9816, but let's punch it in just to make sure. Sine of 79, and there it is. Why does that come out to the same? Well, because 11 and 79 are complements. So the sine of one is going to equal the cosine of the other. I could switch them, by the way. I could do the sine of 11 and the cosine of 79 degrees. Sine of 11, cosine 79. Notice both of them are 0.1908. Let's find the tangent of 64 degrees. Well, we have a tangent key on the calculator, just tangent 64, close parentheses. Now there it is, 2.050 is our tangent. Before I move on to secant, cosecant, and cotangent, I want to briefly look at the unit circle and talk about our values of sine and cosine here, and tangent. So here's our radius. That radius is 1 unit. The sine goes from that point on the circle down to the horizontal reference axis. That's the sine. Well, the largest the sine could possibly be is if our point was here. That would just be equal to the radius, would be 1 unit. The smallest it could be, I mean, technically you go right here, your sine could actually come down to 0, but it can actually go down here. If it's below our reference axis, it's negative. So the sine can be between -1 and +1. So we could, if you put in sine on the calculator, it gives you something like 1.45. You know that's wrong because the sine can never be outside of that range of -1 to +1. Well, the cosine goes from that point over to this vertical axis. So we have the same condition. The biggest the cosine could be is if our angle was 0 degrees, that would be 1 unit or equal to the radius. This would be the -1 unit or negative radius. So the cosine goes from -1 to +1 as well. So sine and cosine always have to be in that range. The tangent out here could be 0 if our angle is really small, or if our angle gets big, it can be really big. In fact, if our angle gets close to 90 degrees, it takes a long, long ways for that to creep over and touch that tangent. Going down, it can be very negative. So the tangent of an angle can be any value from -infinity to +infinity. So up here, it makes sense that all of our sines and cosines were 0 point whatever, and our tangent being 2.054 makes sense as well. If I do the tangent of 20 degrees, tangent of 20, I can still get a result that is smaller than 1. 0.3640, that comes to, if I round it to 4 decimal places. 0.3640 is the tangent of 20 degrees. Let's take a look at our secant, cosecant, and cotangent. Secant of an angle is the hypotenuse, length of the hypotenuse over the length of the adjacent side. That is the reciprocal of our cosine. The cosine is the adjacent side over the hypotenuse. So the secant literally is just the reciprocal of the cosine. So if I want to find the secant of 24 degrees, what I can do is I can do 1 divided by the cosine of 24. So on my calculator, I can type in 1 divided by cosine 24. That is the secant. 1.095 is what that'll round to. There's a simpler way. Your calculator has a reciprocal key built into it. On most of your calculators, it looks like this. X -1. Some of your calculators, if you have an older one or a Casio, it might look like that, 1 over X. That takes the reciprocal of what we've calculated. So the way we can enter this, rather than having to do 1 divided by the cosine of 24, I can just do this. Cosine 24, close the parentheses, and then hit that X -1 key. So let me show you. Cosine 24, close parentheses, X -1. Some of your calculators will show the full X -1. Mine just puts that little -1 power there. I hit equals, it's 1.095, exactly what we had here. Do not confuse that with the keys on your calculator that say sine -1, cosine -1. Those do not do the secant. So stay away from those for now. We'll talk about those next week as to what they do. The cosecant of an angle is the length of the hypotenuse divided by the length of the opposite side. Well, if I look at the sine of an angle, the sine is the length of the opposite side divided by the length of the hypotenuse. So here again, the cosecant is literally the reciprocal of the sine. Be careful with these reciprocals because it's kind of backwards from what you would think. Secant goes with cosine, cosecant goes with sine. You would expect it to be the other way around. You'd expect cosine to go with cosecant. They do not. That is not true. The secant goes with the cosine. Cosecant goes with the sine. So they're backwards there. So to find the cosecant, if I want to calculate the cosecant of 66 degrees, I could do 1 divided by the sine of 66. This is going to give me 1.095. Let's double check that. 1 divided by sine 66, 1.095. But again, I could use that reciprocal key to make this a little bit easier on us. Where'd it go? Here we go. I could do just sine of 66, then do that x negative 1 key outside the parentheses like that. So sine 66, close my parentheses and hit the x negative 1, and there it is, 1.095. Now I purposely selected these angles, 66 and 24 here are complements, so that the secant of one would equal the cosecant of the other. The cosecant is still a cofunction. So it is still the cosecant of 66 will be the same as the secant of its complement, the 24. Cotangent is a little bit easier to remember. Cotangent of an angle is the length of the adjacent side over the length of the opposite side. Recall, tangent of an angle was the length of the opposite side over the length of the adjacent side. So again, cotangent is literally the reciprocal of the tangent. So if I wanted to find the cotangent of 29 degrees, I could do 1 divided by the tangent of 29 degrees. 1 divided by tangent of 29, and I get 1.804. But I could do that shortcut again. Tangent 29, close my parentheses, and hit the x negative 1. Tangent 29, reciprocal. I get the same answer, 1.804. This way of doing it, using that reciprocal key, it might be a little harder to understand why it works right now, but getting used to doing it, that will make it a lot easier when we go the other direction to do inverse functions, to get from the value of the sine back to the angle itself, because we have to almost use that x negative 1 key to go the other direction. A note on the value of the cosecant and the secant. We said the sine and cosine are always between negative 1 and positive 1. Well, the secant and cosecant always go outside the circle. So the radius is 1 unit. The secant and cosecant are always outside of the circle. So the secant is either less than or equal to negative 1 or greater than or equal to positive 1. It cannot be between negative 1 and 1. And it makes sense because it's the reciprocal of the cosine. If the cosine is always between negative 1 and 1, 1 divided by the cosine is always going to be outside of that range. And the same is true for the cosecant. Cosecant of an angle is either less than or equal to negative 1 or greater than or equal to positive 1. And of course, the cotangent, once again, can be any value from negative infinity to positive. So, what we really need to do is to practice some of this. I know we have about half an hour left, but I'd rather get you guys practicing this than load you up too much before the weekend. We'll review this on Monday and do much more of it on Monday. So your homework is out of the big book. Page 841 to 843, exercise 33-2. This is our basic trig functions. Page 845 through 846, exercise 33-3A, and page 847 through 848, exercise 33-3B. I'd like you to do a pretty good set on each of those. Make sure you are very familiar with entering these in the calculator to find them, find the trig functions, and using the links of the sides on the sides of the triangle to find those trig functions. We will go over it again a little bit more on Monday. For now, hopefully I left Scott a list of your missing quizzes and stuff. Hopefully each of you got that yesterday from him. We'll take our last 25 minutes here or so to work on the homework. And if you want to work on those quizzes, I will be here to answer any questions for you. Otherwise, that is all the new material I wanted to cover.